Hi everyone, welcome to Bowl Learning. Today we will discuss about the analysis of T-beam, reinforced concrete T-beam reinforced with structural steel. So at the very outset, if you have not already subscribed to the channel, please do subscribe. So let's move on with the design of a cross section. So the cross section that I'm going to model is as shown in the figure. It is as shown in the screen. It has a flange of 1 meter width and a thickness of 150 mm, and we have a web which has a width of 300 mm and the web height of 500 mm. The span that we are going to model is 5 meters. So let's quickly jump into the ABAQUS software. So at the very outset, what we have to do is to create a model. So for that, we double click on models. We name the model here. Let's call it T-beam. Click OK. Now we can see that the model has been created. Now we create parts. Now before we move ahead, I would like to just remind you that the procedure that we follow to create the model, to apply the loads and to take out the result is all arranged in the way that we see here. So at the very outset, we just create the parts. For example, when I say parts, I mean by the T-beam cross section itself, the concrete, the reinforcing bars, stirrups, and so on. So then we assign material properties such as the concrete material property. We give the constitutive relationships for compression as well as tension, damage parameters, and so on, and also the behavior of steel, and followed by assembly. In assembly, we bring things together. So first we bring in the beam, and then we start bringing in all the rebars. We can duplicate the rebars, duplicate the stirrups, and so on. And then after that, we assign steps. A step is where we designate the boundary conditions, the type of load, the type of displacement, and whatnot. And then interaction is where we specify interaction between the parts. This could be friction or heat or whatever. And then we have load. Then we specify the mesh, which mesh should be, what is the element type, what is the element size. All this information is provided here. Then there is optimization followed by job. It is this section where we submit the job, where we let the software to start analyzing and solving the finite element problem. And then followed by that, we have visualization. In visualization, we see our results. So let's move into parts. So to create the first part, we need to double click on parts, and let's call it T-beam. Now I'm going to create my T-beam itself, that is made of concrete, but I'm just creating the part straight away. And I'm going to make it as a solid, deformable solid, and I'm going to use extrusion. When I say extrusion, I mean that I specify the cross section, and then I specify the distance to which it has to be extruded. That is, the plane turns into a we essentially use some lines to create a closed surface, and that surface is extruded to create the solid. So that is done here. Now the approximate size is not very important, but for the purpose of snap and ease, it is always good that we give an approximate size. And the best way to do that is just to multiply just to see what is the largest cross-sectional dimension that we have. In our case, it is 1000 mm, so it's always good to provide 1000 times 2, which is 2000 mm. So our grid is ready, and we are going to create the cross section. So we already saw the cross section from the paint image, so I'm going to just show it to you again. We have 300 width, 500 depth, 150 and 1000. So I'm going to create my web. So I just draw a line approximately, and then I select this add dimension. I just click here, and fortunately it is 300. If it is not 300, we just enter 300 and enter 300 here, and then it becomes 300. And then now we draw the 500 mm line. So just randomly draw something, also draw one more here. There are 100 ways in which this can be drawn, but I'm just doing one of it. And then we have the measure, because we want it to be 500, so just type 500 here, type 500 here, turns into 500. And then we have 350 on either sides, 150 upwards, and then we complete that. So what I'm going to do is I'm just going to hit there, and then I type 350. Sorry, I click here, I draw it, then again I click here, I draw it. So I'm going to give my dimensions as 350, dimension is 350, and then I'm going to make it, let's give the measure as 150, one more line here, or I can just draw a line from here, join this. So we have created the cross section. Now all that we have to do now is to just click done and specify the length to which we need to extrude. So we need to extrude it by 5000 mm, that is 5 meters. So we have created the cross section here. Now I just want to create something called sections. I want to divide this solid into sections for the purpose of applying the boundary condition, applying the loads. So what I'm going to do is I'm going to create a few sections. So the first section that I'm going to do, creating a section doesn't really mean that you split the object. We're just creating a section plane inside, which does not really affect the homogeneity of the material. So it is just for the purpose of meshing and so on. So I'm just going to create a plane here. I want to cut this in this plane, so I'm just going to give extend face. I'm going to click this face, create partition. So I've created this partition, and then I want to create 3 more partitions. One partition in the center where I'm going to apply the load, and then 2 partitions here where I'm going to, at the bottom, where I'm going to specify the boundary condition. So now I'm going to create a datum plane. So hit hold on this one. So I click this plane because I just want to offset this plane, enter value in the opposite direction, let's say 200. So I created a plane there, and on this side also I want to create a plane here, enter value, okay, let's call it 200. So I've created 2 planes, and I'm going to create one more plane which is going to be at the mid span, which is 2500 mm. So I've created 3 planes. Now I'm going to cut them. So we have used datum plane option. We want to split this, create the partition, click OK. Then again this cell, click on the partition and the plane, it cuts it there. Again select this one, select on the plane, hit OK. So we have created a few sections which are going to be beneficial as we progress. So this is the concrete part of it. Now we are going to create a few reinforcing bars. So the first one is going to be the longitudinal bar itself. So I just call it long bar, and it's going to be wire planar because I'm going to assume steel to be a wire element, and since I'm going to assign a truss property to it, which means that it does not take bending, it is just takes compression and tension only. So just click on continue, click on this, just randomly draw a line, and click over here and get 5000. Now if you want to consider cover as well, you might have to reduce according to your case. You might have to reduce 50 on either sides, but I'm just going to give uh, the entire length. So that creates our first element. So you can see that we have first rebar, and next rebar is going to be the stirrup. So let's call it stirrups. So it's going to be again wire element, and the easiest way to do that is to just draw a rectangle. And what are the dimension of these stirrups? Let's go to this image. Assume that I'm taking 50-50 cover from either 25-25 from either sides. So that's going to give me 250 over here, and it's going to give me this is 500 plus 6 plus 110, that's 650 minus 50, which gives me 600. So it's 250 by 600. So I'm going to go hit this. It's going to be 250. This is going to be 600. So we have created the stirrups. Done. And then we are going to also create a few transverse bars. These are not as per any design, these are just for the sake of filling that space. So that's, let's call it transverse bar. Let's make it small for the convenience. So transverse bar wire. Okay, so I'm going to give a length of 1 meter because that's the width of the flange. Let's go. So that we've created it. Done. Now the next step, now we have created all the parts. Now we're going to create the materials. So there are basically two materials. We have the steel as well as the concrete. So steel, assigning steel is very easy. So it is just name it as steel. The density is specified in ton per mm cube. So if you go into the ABAQUS documentation website, we'll see that there are a set of consistent units that we might have to follow. For example, if you're going to use the SI unit with mm, the density has to be specified in ton per mm cube. Your length should be specified in mm. Your stresses should be specified in Newton per mm square. Force should be specified in Newton, and so on. So there is a consistent set of units. If you don't follow these, your results might not be very correct. So it's always good to follow a consistent set of units. So the density of steel is 7,800 kilogram per meter cube, but when we convert it to ton per mm cube, it becomes 7.8 E minus 9. And then elasticity, we specify it in MPa, so you know that it is 210 GPa, which turns out to be 210,000 MPa, and we give a Poisson's ratio of 0.3. and plasticity, so we are going to assume that it's going to be elastic perfect plastic. So let's specify 450 MPa as yield stress at 0 plastic strain. So we have specified steel. Now we are going to specify the concrete. The concrete damage plasticity model is the one that we're going to use. So before that, we have to specify the density. The density of reinforced concrete is 2.4 E minus 9, that is 2,400 kilogram per meter cube. And then we go into elasticity. So the concrete damage plasticity model that I'm going to use is based on a model that I found on the internet. It is I'm going to use this sheet. So in this sheet I have several values like 25, 35, 40, 43, 45, 50 MPa and so on. So I'm going to use 25 MPa concrete. So this has listed all the values. So I can just copy paste these straight away. So I'm going to hit copy. I'm going to paste it here. Now I go into mechanical, then I go into plasticity, concrete damage plasticity. So we have to specify these CDP parameters. So these are some of the default values. I'm just going to copy paste these. And then I have yield stress in elastic strain, so I'm going to copy this straight away. I'm going to paste this here, and sub options we specify the damage. This is actually the part which gives damage, which means that when the concrete has crossed a particular level of stress, it causes damage in the concrete and it is not recoverable. So the capacity of those parts of the structure is lost. So that is really what damage does. So we just copy it as it is, paste it here, click OK. We see that to see the tension behavior, to specify the tension behavior, and also to see the tension cracks, we have to specify these. Copy these again, copy, sorry, so that is here, and hit OK. So we have specified the materials. Now we need to specify sections. When I mean section, you can understand that sections actually help us to reduce computational effort. For example, we assume the bars to be wire elements. So for that we have to specify a wire element section, a truss section, so that it can be directly applied onto the part. And for the steel, for the concrete, we have to specify a homogeneous section, so that the program boils, simplifies its calculations based on that. So the first one is the concrete section. It is homogeneous, it is solid, continue, and the material is concrete. The next section is steel, rebar. This is going to be the truss section, so I'm going to use beam. In that we have truss, continue, the material is steel. This is the cross-sectional area in mm square. So 8 mm bars, if you find the area, it's 50.24 mm square. I'm going to assume all bars as 8 mm bars. So it's that's it. Now I have to assign these sections to the parts. The longitudinal bar, you just have to click this, select it, click done, click OK. So it turns green, so that means the section has been assigned. Now the stirrup, again we have to select it, click done, rebar, OK, the section has been assigned. Now the beam, double click, this is a solid homogeneous material, so select this, concrete, OK, and finally we have the transverse bars, click on this one, done, steel rebar, OK. So we have assigned the materials. We have so that's done. Now the next step is assembly. We want to bring things together, so I'm just going to hit on assembly instances. So these are the parts that we had created. So you can import as many as parts as possible. You can as required. You can, for example, in this case I'm going to use multiple stirrups, multiple transverse bar, multiple longitudinal bars, and so on. So for the sake of starting, I'm just going to select all of these. I'm going to import all of these, and whichever needs to be copied, duplicated, we will do it as we go ahead. Now if you click on this, it will be separated at a distance. It won't, because if you don't do this, it all comes at the origin. So we want to just give it an offset for our convenience. So when you turn it around, you can really see the section. So the first thing that I'm going to do is I'm going to fit my my stirrup in place. So what I'm going to do is I'm going to specify a point here, so that I can just drag this the stirrup and just drop it there. So for that purpose I'm going to use this one. I'm going to create a data point. Now you can see from this figure that it's a this is like based on a reference point. So this is going to be my reference point. I want this point to be on this plane at 25 in y and 25 in minus x. So it is minus 25 comma 25 comma 0. That point is created there. So all I have to do now is just to select this. Done. I have to translate this from here and I'm going to drop it here. Okay, now we will adjust it inside as well, so just for the time being we is keeping it here. And also now we need to bring this bar as well. This bar is oriented in along the x-axis. We want to just rotate it. For that I use this tool. I'm sorry, I did not click OK for that. So just I'm going to repeat it again. Select this, click on this corner, paste it here, hit OK. So that places it there. Now I need to rotate this element, this part. So I have to specify the axis about which I'm going to. So this is the axis about which I'm going to rotate it. I want to rotate by 90 degrees. Click OK. So that really has done the job. Now I'm going to move this to this point, because we have, according to our problem, we are going to use 3 rebars here, 3 bar, and a few here as well. I've not specified because I don't know the exact count. So just I'm going to move it here. So I'm just going to select it, click on this point, zoom it in, keep it here. So I've kept the rebar there. Now the thing is, we have to hide this element, this part now. This instance has to be hidden. It has to be hidden for us to continue. So what we do is click on this option, then cells, just or you can just click on this. We have instances, and then we click on T-beam and click remove. So that really hides it. Now I need to make copies of this, so I'm going to use this tool. So what is the distance here between these? This is 250, so 125. So I'm going to use this tool to create some copies. Done. I want to create 2 more here. So I select this, make this as 1. I want to move it by 125 in the opposite direction. I want to make 2 of it, and in this direction I want to make a copy also. So I need 2, but now I have to specify the direction about which I need to make it, and this is going to be 600. So it's going to be flipped around, and I made the copy here. So click on OK. So now I have got the rebars here as well. Now I need to create copies of this stirrup. So I'm going to use this tool again, select it. Let's give a spacing of 200 and C. Specify the direction, the opposite direction. Keep adding it if you don't know the number until it reaches the other end. Okay. Done. Now, if we want to remove these stirrups at the end, what you have to do is we have to just go here. The first stirrup is over here. Stirrup is over here. Just delete it because we don't want the stirrup to be seen on the surface. And the last stirrup is over here. Just delete it. So that makes it a little more professional. So we have created it that way. Now I need to move this. I just hit the center midpoint. Let's go copy it there. Let's do it again. Select this. Done. midpoint. I'm going to copy it here. So click on OK. Now I need to make copies again. I'm using the same tool. Click on OK. I'm going to use 200 again. I'm going to specify my direction as this one. I'm going to make a lot of copies. The last one. Okay, so that's done. I need to create copies of this longitudinal bar as well, so that it fills up the space. So I'm going to use the tool again. Select this, dismiss. Let's keep it as 200. Sorry. So that pretty much creates a bar there. So click on OK. Again, I'm going to use this tool to translate this one. I'm going to use 200. I'm going to specify my direction here. So that's enough. Okay, so we have created the reinforcement cage. We can just unhide the section so it's all inside. So if you want to make this solid a little more translucent or a little less a little more transparent, you can just hit this button and you can adjust the transparency so we can see where the bar is, just to make sure that things are has come up as you have anticipated and so on. So that really finishes up the assembly part. And the next part is going to be steps. So we are going to specify the boundary conditions and also the loads. So let the boundary condition be pinned here and roller there. Okay, so I specify my boundary condition. The first one, it is a displacement boundary condition. So I specify, I just turn it around, I select this, and I say that I need to restrain all motions in X, Y, and Z. So this is like a pin boundary condition. The next boundary condition is a roller. Let's call it a roller. So I hit this one, click on OK. Now I want as you can see, I want it to move in Z direction, but I don't want it to translate in any other direction. So I just click this too. So that really creates this boundary condition. Now what I have to do is to apply the load. Now this is you can apply a load or you can apply a displacement. To get the load displacement curve with the capacity of the cross section, what we usually do is we apply a displacement and then we see the response of the or the reaction. So when the reaction drops, it means that it has lost capacity and so on. So we are going to apply a displacement of say 5 mm. So what I have to do is just click on step. You need to add a step now, so we cannot add displacement here. So I'm also going to use dynamic explicit, continue. Now there is something called mass scaling, which has to be used with care, because you cannot give a very high value of mass scaling. Mass scaling speeds up your analysis, but it really sometimes compromises the accuracy of the results. So just for the sake of doing the problem, I'm going to use 1000 as the mass scaling. Hit on OK. That's it. And then I'm going to apply my displacement. So again, since it is a displacement, it is a boundary condition, displacement boundary condition. If you want to apply a load, you can just do it right here, but this is going to be a displacement. So I hit on displacement. This is in displacement, continue. I specify the I'm going to apply the load here. So click done. I need to apply a load in U2, so I'm going to give -5. Now also you have to specify an amplitude. In static general you don't have to specify this because the solver assumes the model to be in a static type of loading, quasi-static type of loading, so there is no effects of inertia but in dynamic explicit the effect of inertia is considered, so we have to also specify the rate at which the load is applied. So it is instantaneous will not work. If you hit this you can see an error message, so we have to create an amplitude just for 1 second. If you have noticed before, the step time is 1 second, so just let's create a small table that when time is 0 the amplitude is 0, when time is 1 let the amplitude be 1, so whatever is the displacement you can just multiply it with it. So by the time 1 second is over we reach 5 mm displacement. Now we have to apply this one and hit OK. So now we have specified steps as well. Now to see the output, and if you want to see something like damage, you have to go into field output, you have to click on tension damage and compression damage. If you forget this and you do the analysis, this won't be displayed, so you have to do the analysis from beginning, so don't forget this. Click on OK, and now something that is left is constraints. We have to assume this constraint in the sense we have to embed the rebars into the solid. So for that we have to use a constraint where we use embedded region, continue, and we have to select the embedded region. The embedded region is the rebars, so we have to just hide the beam here, select all of these, done. The host region, just if you click this you can flip it, select your, you have to select the region, select this, done, OK, and hit view all. So this is the constraint that we need to apply, and the final step is to create a job and submit the job. So I'm going to name it as T-beam itself, continue. You can use parallelization to speed up your analysis, OK, and just submit. That's it. If there is any error it will be shown here. You can see that the following parts are not meshed. Yes, we forgot to mesh the thing, so we have to go into mesh. We're going to select mesh it part by part. Let's go into the longitudinal rebar. This is where we set the mesh size. I'm going to use a mesh size of 50 mm for the bars and say 25 for the beam. So when you click this, now it is meshed. Go to stirrup, again I'm going to use 50, apply. T-beam I'm going to use 25 just to get a smooth result, smoother curves. So that is the mesh. Now this is the benefit of really creating a section here. If you don't have this section, it might look a little weird sometimes. So transverse, again I need 50 mm size here. OK, I'm just going to mesh it. So let's submit it again. You can see that it is processing. It has been submitted without any errors. So if you want to see the status, all you have to do is hit on monitor, and then this is where we see the log, we see what's happening, we see some of the errors. If there is an error, you will not get the result, but if there are some warnings, it's okay, because they'll just notify you some of the assumptions that the software has done, which might not be harmful as it is. Just nothing to worry about. element 2976 missing properties, missing section. Let's see what has gone wrong there. I mean, this happens when it comes to analysis. Yes, we also in the mesh there is also something that we have to do, is to specify the element type. So this is truss element. We forgot to apply the element type. Let's do it for all of it. Truss, stirrup, done, truss. Okay, and for the T-beam, select all of it. This by default is C3D8R, so that is nothing to be changed. Let's submit it again. Okay. Let's check the monitor to see how things are going. Okay, the ABAQUS explicit packager has started, which probably means we are on the safe side. Let's wait for a few moments just to make sure that we're going to see some of the steps, and then we will wait until the analysis is over. Okay, we can see that the first step has been complete. We can see the time that it took to solve the first step. And let's wait until it is complete. We will have to wait for 20 steps until it is done, because the step is 0.05, it's 0.1 up to 1 second. So let's wait until it is complete. Now, just before the analysis is done, I just want to say that there are a few things that you can do from here. That is, you can kill or abort the process here. It will ask if you want to stop it for some reason. You found that you did not do it properly. You can just hit this. Dismiss will just close this window, but we can always open it from here. So let's wait for a few minutes for it to be over. We can see that the analysis is complete. Let's go into visualization. For that, just right click on this, hit on results, and we are here. Well, this is where we see the results, see some of the things. For example, the first thing I just want to see is how the cracks has appeared. So I have to go here and hit on damage T, or the tension damage. You can see how some of the cracks have appeared. Now, if we had given a 4-point loading, we could have seen more vertical cracks here, followed by some more shear cracks in this region, and so on. Then when you look at compression damage, there doesn't seem to be any. When you look at stresses, when you hit maximum principal, when you just go into, because you hide the rebar and look at the T-beam alone, you can see that the bars are in a state of if you go into S11, you can see the stresses in bars. These bars are in tension, these bars are in compression, and these have already yielded. And then let's also see what are the stresses in the concrete. Maximum, when I look at maximum principal, you can see some of the stresses here. When I look at the nieces, you can see some of these. You can see how let's look at S11, or let's say S33. You can see how the stresses are evolving. You can see that initially there is tension over here, and then as we progress there are cracks which releases some of the stresses there, and this is how it is plotted. So I hope you have benefited from this video. Please consider subscribing to the channel and also recommending it to your colleagues. Thank you for watching. Please stay tuned for more videos.